Okay, everyone, we're gonna get started. So jumping into tonight's PowerPoint, we're gonna go over kind of the last remaining topics from chapter 6, our thermochemistry chapter for this semester. Okay, so we're gonna start out, like always, going over the challenge problems from last session, so Monday's session. Okay, and the first one, it's a coffee cup calorimeter question, right? We have 115 milliliters of water that warms up 4.3 degrees Celsius, and they ask how much heat did the reaction evolve, right? I said evolve because I didn't want to tell you whether the reaction itself should have released or absorbed heat, which remember, if the reaction's releasing heat, the Q value would be negative, indicating it's exothermic, while if the reaction absorbed the heat, it would be an endothermic reaction, which has a positive Q value. Okay, so it is important to distinguish that. So remember, in a coffee cup calorimeter, right, we basically have a coffee cup full of water, and we're going to measure the temperature of the water. Okay, and so we put our reaction in the water, and if the water is exothermic, meaning if the reaction gives off heat, then it's giving that heat off to the water, causing it to heat up. Okay, so that's the circumstance we see here. The water's heating up, okay, and that water has to be getting that thermal energy from our reaction, okay? Somebody asked if there's a challenge problem before this. There's one that I moved to a challenge problem, but I like to go through my multiple choice first. So we will get to all the challenge problems. Obviously, we can only. Okay, and so we're going to say, so we should know based on the water increasing in temperature that the reaction should be giving off heat, right? It's releasing it, which is telling us it should be A or B, right? Because the reaction has to be giving it off. It should have a negative sign if the water is heating up. Okay, and so we were told a lot of information about our water, which in a coffee cup calorimeter is our surroundings. So the mass of the water is 115 grams. We know that because 115 milliliters, using the density of water being 1 gram per milliliter, it's just 115 grams of water. Okay, the specific heat capacity, C of water, is 4.184. That was given. And we were told that the temperature increased by 4.3 degrees Celsius, right? So because the temperature increased, when we do the change in temperature, which is our final temperature minus our initial temperature, right? Because it increased and it's final minus initial, it's going to be positive 4 degrees or 4.3 degrees Celsius as our change, not negative, right? Because our final temperature, if our temperature increased, will be higher. Therefore, the change will be positive, not negative. That is a big key to this problem. Okay, and so how much heat does our water have? Well, Q, or heat of our water, is equal to our mass times our specific heat capacity times our change in temperature, right? So I input those variables, and I find my heat of water is positive 2,069 joules, right? And so remember, in a coffee cup calorimeter, we have two different sides, right, in terms of heat. We have the heat of our surroundings, or the heat of our water, and the heat of the actual reaction itself. And remember that they're equal in magnitude, so their numbers the same, but their signs have to be opposites. Okay, and so if the heat of our water is positive 2,069 joules, that means the heat of our reaction has to be negative 2,069 joules. Okay, so that was the answer, and I believe that corresponded actually with A, which is the same number, it's just in kilojoules, right? So a negative 2,070 or so joules is equal to negative 2.07 kilojoules. Okay, so A should have been your answer for that. Okay, number 2. Okay, and this is actually a question that they've asked over and over, and so you're told that you 15.2 kilojoules of heat is put into 62 grams of zinc silver, and aluminum. Okay, and what that means is that these are endothermic reactions, right? Maybe an oven, some outside heat source is putting in thermal energy into 62 grams of 3 different metals to heat them up. Okay, so all of them are in an endothermic reaction, and you're told that they all had an initial temperature of 0 degrees Celsius, right? So we had cold metals and we're heating them up with 15.2 kilojoules of heat each. And if in this circumstance, they're asking which one of the following metals would have the highest final temperature. Okay, and the answer to this is B, silver. Okay, and let's look at our equation here. Okay, and so remember Q, our heat, is equal to M, our mass, times our specific heat, C, times delta T. Now we're told that the heat put into this system, right, it's going to be a positive Q value, is 15.2 kilojoules, which is 15,200 joules. Okay, and that'll be equal to, well, the mass of all of our metals is 62 grams, right? That's not going to change from metal to metal, times our specific heat, times our change in temperature. And we know that the original temperature, our initial temperature for all of them, is 0 degrees Celsius, right? So the only thing that's going to change between these two are their final temperatures and their specific heat capacity. Okay, and we can see when looking at this equation the relationship between these variables, right? If the value of our specific heat our specific heat capacity decreases, that means our change in temperature has to increase, right? Because it's a fixed amount of heat and a fixed mass, right? So as C decreases, delta T increases. And because the initial temperature for all of these are 0 degrees Celsius, that means that as our specific heat capacity decreases, our final temperature is going to increase. And so which of these options has the smallest specific heat capacity? That was silver. And so silver would have the highest final temperature. Okay, if you also plug in, that's how you kind of theoretically approach this problem. But if you wanted to plug in the specific heat capacities of each metal individually and solve for your final temperatures, these numbers are what you should have gotten. Okay, so if you did the math out, you'd find that zinc's temperature would increase to 633 degrees Celsius. Silver would go up to over 1,000 degrees Celsius, and aluminum would only increase to about 272 degrees Celsius. Okay, and so if you plug in the numbers, you can also see that silver would have the highest final temperature. But you can also use the relationship between these variables to see that the metal with the lowest specific heat capacity should have the greatest change in temperature, which, because they all have the same initial temperature, the greatest change in temperature would yield the highest final temperature. Okay. Again, that is a type of question that's very reoccurring from year to year. Okay. So moving on to the third one, you're told that the change in enthalpy for a 3-step reaction is 8.42 kilojoules. The enthalpy for the first step was 43.02 kilojoules, and the enthalpy for the step 2 is negative 18.49 kilojoules. I apologize that that minus sign is on a different line. What is the enthalpy of the third step? So this is basically one of those Hess's law questions that we did at the end of last session, but just looking at the numbers. Okay, and what we learned from Hess's law is basically the enthalpy change for an overall reaction, which is given as 8.42 kilojoules, right? The overall change in enthalpy is 8.42, will be equal to the sum of the enthalpies from each individual reaction, right? So 8.42 kilojoules would be equal to 43.02 kilojoules, which is the enthalpy of our first step, plus negative 18.49 kilojoules, the enthalpy from our second step, plus some unknown enthalpy of our third step, right? So again, the overall delta H is positive 8.42, and I just wrote our known Step 1 is 43 kilojoules, step 2, negative 18. And all I do is solve for x, which is the enthalpy change of our third step in this reaction. And I find that for the sum of steps 1 through 3 to equal the overall delta H, that the enthalpy of our third step, which I denote with x, would have to equal negative 16.11 kilojoules. Right? We're basically just adding up the enthalpy of these 3 steps to make them equal to our overall delta H. Any questions on the content of the first 3 questions? They're all very, very common, typical thermo questions. Okay. So moving on, hopefully you saw my edit that I sent out. I tried to change this equation a bit to make the math a little bit more complicated, but what I didn't notice is that our sodiums weren't balanced. And so I messed up, and so I put it back to the original coefficients in this balanced equation. Okay, so I did post that. I'm sorry if you did not see it, but the coefficients should have been 1, 1, 1, and 2. This is the balanced equation you should have been using. I'm also going to make one other comment about this problem. It's not my favorite problem because we're kind of switching from heat to enthalpy, right? We're doing kind of coffee cup calorimeter stuff and then enthalpy for the entire reaction. You don't really see these 2 topics combined in this way because, again, enthalpy and heat aren't necessarily the same thing because heat can also involve, again, a change in volume. So I kind of apologize. This was kind of an overzealous problem, me trying to combine topics. And so this would typically be 2 separate problems, right? They don't typically combine the coffee cup calorimeter aspect with the enthalpy change of a reaction. You just don't really see that. But anyways, kind of going into the problem and what I was hoping you guys were to get, would be able to get of this is, right, so you're told 18 grams of nitrogen dioxide, or NO2, gas are placed in a coffee cup calorimeter. Okay, in this coffee cup calorimeter, there's 135 milliliters of water, which cools down 0.785 degrees from the original temperature of 30 degrees Celsius. What is the enthalpy change for the overall reaction above? Okay, and what I was hoping you guys were going to kind of do is use the information about water to basically find your overall heat of water and then apply that to the reaction. Okay, those are kind of your first 2 steps out of 3. So before getting ahead of myself, let's look at water. Okay, so water, again, in a coffee cup calorimeter is going to be considered your surroundings. Okay, and so the mass of water was 135 grams, right? Because we had 135 milliliters, and using the density of water, we can convert it to grams. C, our specific heat of water, is a value I'm sure you're getting used to, 4.184 joules per gram degrees Celsius. And then our change in temperature was 0.785 degrees Celsius. But notice that it said the temperature lowered. Okay, so the temperature decreased 0.785 degrees Celsius. That means when you do your change in temperature, which is your final temperature minus your initial temperature, right? Because your temperature decreased, that means your final temperature will be less than your initial temperature, which means your change in temperature will be negative anytime you decrease in temperature, right? So it's a negative 0.785 degrees Celsius. Okay, and so what's the heat of our water or the heat of our surroundings? Well, the heat of water is the mass, 135, times the specific heat times our change in temperature. And what we'll find is that the Q of water is negative 443.4 joules, meaning water lost 443.4 joules of energy. Okay. Now, remember that thermal energy is conserved. Okay, and so if this amount of energy is lost from our water, it has to be gained by our reaction, right? And that's basically said by this statement. The Q of our water is equal in magnitude but opposite in sign to the Q or heat of our reaction. Okay, and so we find that the heat of our reaction is positive 443.4 joules. Okay, and this is the amount of heat, the positive means absorbed, that this is the amount of heat that is absorbed whenever 18 grams of nitrogen dioxide reacts, right? Because they said this information is when 18 grams of NO2 reacts, okay? So after getting to this part, you have one last step, right? They ask what is kind of the heat or enthalpy change for the entire reaction, right? Let me go back. For this entire reaction listed. But notice that your delta H, your change in thermal energy for this reaction, is in terms of moles, right? It's in terms of almost the molar ratio. And so in terms of NO2, right, they're asking what's the enthalpy change when 1 mole of NO2 goes through this reaction, okay? And the amount we solved for is how much heat is absorbed when 18 grams of NO2 reacts, okay? And so we want to find out how much how much heat 1 mole of NO2 is responsible. So 1 mole of NO2, we multiply by its molar mass to find grams of NO2. And then we know that every time 18 grams of NO2 reacts, 443.4 joules are absorbed. And this tells us that 1,133 joules will be absorbed, right, because it's positive, whenever 1 mole of NO2 reacts. Okay. Again, these would typically kind of be like 2 separate problems. They don't really typically combine these. But are there any questions on this problem? So number 5 is a very classic heat exchange problem, right? So you're going to have species that lose heat and the other species are going to gain it. So typically we see this as a beaker of water and a hot metal will be added to it, right? The metal will cool, the water will warm. Okay, now this problem is a little bit more complicated because there's actually 2 pieces of metal that are added, right? You're told that a 27.25 gram of hot silver metal is added and 38 grams of hot copper are added to this beaker of water, okay? Then you're told that they all reach thermal equilibrium at 19 degrees Celsius, right? So their final temperature will all be 19 degrees Celsius. And in the end, you are asked, what was the initial temperature of that silver metal that you added, okay? So there's a lot of information, so we're just going to kind of break it down, okay? And so let's look at the top. And you'll typically see Q of system equals negative Q of your surroundings, right? Saying that any heat lost from your system is going to go to your surroundings, or any heat from your surroundings that is lost is going to go to your system, right? They're flow in opposite directions. Okay, but we have 3 different species here, right? We can't just write Q of water equals negative Q of copper, right? Because we also have to account for the silver. And so because they tell us we add a piece of hot silver metal, I'm initially going to assume that the silver, when it's put in the water, is going to lose heat, and it's going to be kind of exothermic in nature. Okay, and so using this general equation, Q lost equals negative Q gained, which is basically what you guys have been using. I just put different words here, right? Well, what's our species that's gaining heat? Okay, well, our water is increasing in temperature, right? And if it increases in temperature, that means it must have gained thermal energy. So my Q gained is just equal to my heat of water, okay? And how about the lost section? What's chemical species lost heat? Well, because we added hot copper and silver to cold water, right? I'm going to assume that my heat of lost is equal to my heat of copper plus my heat of silver. Okay, so a pretty typical problem. It's just one of our Q's is actually a combination of 2 different metals. Okay, and so here I'm going to write kind of, I just wrote my temperatures, right? So my water, I know, went from 15 to 19 degrees Celsius. My copper went from 150 degrees Celsius to 19 degrees Celsius. And the temperature of my silver went from some unknown initial temperature, that's what we're solving for, down to 19 degrees Celsius. Again, in a heat exchange problem like this, your final temperature should always be the same for all the species, right? Because they're going to come to thermal equilibrium and all of the same thermal temperature. Okay, so let's focus on what we first do know. Okay, so let's start with the heat of water, or the Q of water. Okay, and so the heat of water will be equal to the mass of water times our specific heat of water times our change in temperature for the water. So what's our mass of water? Well, it was 150 milliliters, which is 150 grams, right? So 150 grams. Our specific heat, 4.184, and our change in temperature would be 4 degrees Celsius, right? 19 divided by 15 is 4. And so when we solve for this, we find that the Q of water would be equal to positive 2,510.4 joules, okay? And Q of water, again, kind of represents our gained heat, okay? And remember, our gained heat and our lost heat are equal in magnitude but opposite in direction. So that means the heat that we lost from our metals, right, would be equal to negative 2,510.4 joules, which is equal to not just the heat of our copper, but also the heat of our silver, okay? And so again, let's plug in information we know, okay? And so this negative 2,510.4 joules would be equal to my Q, or my heat of copper, which is equal to my mass of copper times my specific heat of copper times the change in temperature of my copper, plus the heat of my silver, which again, heat of silver is equal to mass of silver times specific heat of silver times the change in temperature of my silver. Okay, and so down below, all I do is plug in my values, right? So 38 grams of copper, its specific heat is 0.385, and its change in temperature went from, it was 150 to 19, and so our final temperature was 19 minus our initial temperature, 150, would be our delta T. And then we can fill in our information for silver as well, right? The mass of silver is a little bit over 27 grams, and the specific heat is 0.24. Okay, and then our temperature, we know our final temperature is 19 degrees Celsius, and so we label our initial temperature as X. Okay, and when you can kind of just see my algebra from here, right, and continuing down. If anybody has any questions about how I went about this algebra, I'm happy to answer it. But when you solve for X, it would come out to 109.8 degrees Celsius. Okay, and so our silver started, or initially was 109.8 degrees Celsius, and then went down to 19 degrees Celsius when the silver and the copper were added to the water. Okay, the big key to this was knowing that the Q of water would be equal in magnitude but opposite in sign to not just copper or silver, but actually the sum of them both, right? Because these together are kind of like the total heat that's lost, and what absorbed the heat that was lost, it was the water, which gained that heat. Questions on this one before moving on?
Yeah, in the problem description, you had each of the specific heats listed as joule per mole instead of joule per kilogram of degrees Celsius. Was that like intentional or
Sorry, I missed the very beginning of that.
like can you go back to like the actual question prompt real quick? Like,
No, it was not meant to say mole. Sorry.
okay, yeah, because that had really confused me because I didn't know if we were supposed to,
If you did it with moles, I apologize. If you followed the same procedures, like if you did the general same steps, then it's correct. Yeah, that was an error on my part. These are actually real values, so I get them offline. And so I may have looked in the wrong column because often they will give it as joules per mole C. They'll also give it as joules per gram C. I think I may have just typed the wrong one here, but yeah, no, that wasn't any purpose. That was a mistake.
Okay, thank you.
But again, if you did joules per mole degree Celsius, if you followed the same path and got an answer that's different, as long as your process was actually the same, you know, those values, you should have gotten an answer that was legitimate and made relative sense, even though the actual numbers may be slightly different, because in one formula you're using grams, the other one moles. Okay. Moving on, the last two kind of challenge problems were Hess's law problems, right? So you're going to be given a kind of what I call the goal reaction that you're trying to find your change in enthalpy for, and then you're given kind of a multi-stepped way to get there, and you're trying to manipulate them to get your goal reaction and find your overall delta H. And so this one I'm going to kind of go over first. So just notice the numbers on the side here, just label, you know, so the first one listed I label as number 1. The second one I label as number 2. And these numbers carry down if that gets confusing. Like number 1 will always indicate the same general equation. Okay, and so for Hess's law, I always recommend that when you look at the goal reaction and then look at your sub-reactions, that you always try to identify some chemical species that is unique to one of your sub-reactions. Okay, so let's look at sub-reaction 2 and 3, for example. N2O5 gas is only present in this second sub-reaction. As well as our goal reaction. But out of the sub-reactions, it's only in the second one, which means that's a good chemical to focus on. Okay, so I underlined that, and I also underlined it in the goal reaction. Okay, and then under it, I'm going to write the changes I want to make so that N2O5 appears in my second sub-reaction, just like it does in my goal reaction. Okay, and so basically, in sub-reaction 2, it goes from N2O5 as a reactant with a coefficient of 1. And in our goal reaction, we need it to have a coefficient of 2, and it needs to be a product. That indicates to me that I need to take this entire second sub-reaction, and I have to multiply the entire thing by 2, and I'm going to flip it, right? So my reactants become products, and my products become reactants. Okay? I'm going to do the same thing for sub-reaction 3, right? I'm going to try to identify something that appears in my goal reaction that only appears in my third sub-reaction, okay? And something I identify is that nitrogen gas only appears in this third sub-reaction, okay? And it appears as a reactant with a coefficient of 1. When I look at my goal reaction, N2 is also a reactant, but its coefficient is 2. That indicates to me that I need to multiply this whole third sub-reaction by 2 in order to get my goal reaction eventually. Okay, and so I'm going to make those changes, and I write them down below, right? So 2 here is flipped and multiplied by 2, and 3 directly below it is going to be multiplied just by 2. Okay, and you'll notice for right now, I skipped reaction 1. And the reason I did this is if we try to identify a chemical species that is unique to just equation or sub-equation 1, you'll notice that there isn't, right? Liquid water is also in sub-reaction 2. Oxygen gas is in sub-reaction 3, and hydrogen gas is also in sub-reaction 3. So that's why I skipped it at first. Okay, but now that I know what my manipulations to equation 2 and 3 should have been, which again are written down here, I'm going to look and see, okay, what do I have to do to my first reaction? How do I manipulate it so I get my goal reaction? And one thing I would do, and notice I actually underlined in red here, okay, when I'm looking at my overall goal reaction, I'll notice that there is no hydrogen gas in my balanced equation, okay? And so knowing that there's no hydrogen in my balanced equation, I know that it needs to cancel out in my sub-equations, okay? And so reaction 3, by looking at N2 gas, I knew I had to just multiply it by 2, okay? And I'll notice that another reactant is 2H2 gas, right? Once I multiplied the whole equation by 2, okay? And in my first subreaction, I'll notice that I have 2 molecules of hydrogen gas, but they're on the reactant side, okay? And so in order for these hydrogen gases to cancel, aka be on opposite sides of the equation, therefore not show up in my goal equation, I need to flip this first equation, right? I need to flip it so that my hydrogen gases cancel out and it doesn't appear in my goal reaction, okay? And so that helped indicate to me that I just need to flip my first reaction. So as you can see, it's 2 waters liquid goes to 2H2 plus oxygen, right? And so now I have in in subreaction 3, I have 2 hydrogen gases as a reactant. In subreaction 1, I have 2 hydrogen gases as a product. So they'll cancel out and not appear in my final equation, okay? From here, after knowing these manipulations, and I'll get to the delta H's very shortly, but after knowing that these had to be my manipulations, all I did is I wrote all my reactants going to all my products, right? So I just added up these 3 reactions after their manipulations. And then I canceled out or partially canceled out things that appeared on both sides, right? So oxygen, for example, there are 6 of them as a reactant, 1 of them as a product. Therefore, in our overall net equation, there should only be 5 oxygens on the reactant side, none on the product side, okay? And when we cancel things out as they should, you get at the end the overall goal reaction we were given at the beginning, okay? So that tells you that all the manipulations you did were correct during this process, okay? Now, how do you find the delta H for this reaction? Well, it's important to note that whatever you do to the equation itself, you kind of have to do the same to your delta H value, okay? So whenever you flip an equation, you're going to change the sign on your delta H. So equation 2, for example, was negative originally, negative 73, and then later on it went to positive 147, okay? And the 147 I'll bring in just a second, okay? So again, if you flip your equation, you have to change your sign on delta H. Now, equation 2 and equation 3, we multiplied the entire equation by a coefficient, 2 in each case. Whenever you multiply an equation by a coefficient, you have to multiply your delta H by the same coefficient. Okay, so for sub-equation 2, for example, we had to flip it and multiply it by 2. And so our manipulation to delta H, we should have doubled it and changed the sign. Okay, and you can see down here, that's exactly what we did. It is positive 147 kilojoules. Okay, and so we made those changes. So the delta H of sub-equation 1 should have gone from negative 571 to positive 571 because we eventually flipped it. And our delta H for sub-equation 3 would have had to be doubled. So it's no longer negative 348. It would be negative 696.4 kilojoules. Okay, and so to find the overall delta H, right, you just add up the delta H's of your sub-reactions after you've manipulated them. Okay, so these are our final 3 equations after they were manipulated. Here are their delta H's with their respective changes made. And so we just add these 3 numbers up and it came out to positive 22.6 kilojoules. Are there any questions on that? And we're going to go over another example as well. So here's the other example. I ask you to calculate the standard enthalpy change for the reaction. And then I also ask if 31.5 grams of water are used up, what mass of methane is produced. I think I meant to ask about energy there, but I also have that answer just at the end if you wanted it. Okay, but again, this is a Hess's law question. And so I wrote my goal reaction at the top. So 2 carbon solids plus 2 water gases goes to methane gas plus CO2. And I wrote, again, my 3 sub-reactions. Okay, and so just like before, I'm going to use the same strategy by identifying a unique chemical element in our equation that we also see in our goal reaction. Okay, so in sub-equation 1, we have carbon solid, and this is the only equation we see carbon solid. Okay, and we can see in our goal reaction that it needs to be a reactant and have a coefficient of 2. Okay, so in our sub-reaction, it is a reactant, but its coefficient is 1. So that indicates we should multiply our entire first sub-reaction by 2, including our delta H. And so I did that, and you can see it right here. Okay. For sub-reaction 2, I identified CO2 or carbon dioxide gas as a unique chemical species in that equation. Okay, it has a coefficient of 1 and is a product in our sub-reaction. And when we look up to our goal reaction, it's still a product and still has a coefficient of 1. This tells us that we don't need to manipulate that second equation at all. Okay, and lastly, when I look at sub-equation 3, the chemical species that is unique in this equation would be methane gas, CH4. Okay, it has a coefficient of 1 and is a reactant in the sub-equation. When we look at our overall goal equation, it has a coefficient of 1 but is a product. This indicates that we need to flip our third sub-equation, which means we also need to change the sign on our delta H. Okay. Here's kind of like a list. I'll get to that in a second, but if you were to cancel things out, this would be the overall equation you get at the end, which you'll notice is identical to the goal reaction they asked you to get. And so to get your answer of what your delta H is, it would be equal to the delta H's of all your manipulated reactions. Okay, so if you look, these are the delta H's after the manipulations, and your delta H comes out to positive 15.3 kilojoules, which means 15.3 kilojoules was absorbed, right? Positive means it's absorbed. Okay, and if you wanted to do the math for 31.5 grams of water, it would go to 14.02 grams of methane. Okay, now kind of coming back up to this, I typically write all my reactants going to all my products in kind of an equation format and then cross things out that way. But if you don't like that method, you can kind of use more of a list method, right? So I listed all my reactants. Some of them appeared twice, so 2 water molecules. Then later on, I had another water molecule, and so it became 3. This is just me kind of throwing out another strategy. If you don't like to write the full equation and kind of underline things to see what needs to cancel, doing kind of a list method would also work. Okay, but your answer here should have been positive 15.3 kilojoules. That was really the big part of the problem. Okay, are there any questions up to this point? That was all of our challenge problems from Monday, which has to do with about 70 to 75% of this chapter. No questions? Okay, if there are no questions, just use this time quickly to sign in the chat using your net ID. After that, we will kind of do a very, very quick review of just kind of the equations we use with different topics in thermo, and then we will move on to our last 2 topics, which are the 2 in red on this slide, right? We're going to be doing enthalpy of phase changes and enthalpy of formation. Okay. I will say enthalpy of formation tends to come up more on exams in the past and are typically easier. The phase change problems are typically, I think, one of the more difficult problems in this chapter and they're a little bit more rare to see on the exams, but I think you'll see it a little bit, like somewhat represented, but yeah, it's not like all the questions are going to be phase change problems because it's sort of the most difficult one, or at least in my opinion, one of the more difficult ones. Okay, so if anybody has questions, we're going to be doing kind of a run through of the material. So if you have any remaining questions from last session, this is going to be your best time to kind of ask it, just because we're already kind of going over it. Okay, so a quick review. So we mostly went over heat exchange last time, as well as a little bit of enthalpy. But in heat exchange, I kind of break it down into two broad categories, right? We have metal problems or classic heat exchange. So that's kind of one of the, you drop a hot piece of metal into a beaker of water. And I would say the most important equation you have for this, or the most important relationship, is that the heat, or Q, of your metal will be equal to the negative heat of your water, right? Basically, again, equal in magnitude, opposite in direction. Okay, and so it's knowing that relationship that will help you kind of solve those problems. Okay, calorimeters, again, remember we have two types. We have a basic coffee cup calorimeter, right? And so typically you have a reaction that is occurring in the water, okay? And you'll get some temperature change of the water, and you're often asked about the reaction itself. Okay, so it's important to note that your Q of your water, or the heat of your water, is equal to the mass times the specific heat capacity times the change in temperature. Okay, that's the first relationship you're gonna have to use in these types of problems, but it's also important to remember that the Q of your system is equal to negative Q of your surroundings, right? Again, equal in magnitude, opposite in direction. Okay, and the key for coffee cup calorimeter questions is knowing that your water is pretty much always your surroundings, okay? And so your system is typically like a chemical reaction occurring within that coffee cup calorimeter, okay? And then very similar bomb calorimeters. Again, that second equation is kind of the same. It's a very similar relationship where your surroundings is almost always just water. Just note that the heat of your water, the equation's slightly different, right? It's the MC delta T that you're used to, but in a bomb calorimeter, you also have this second term that's added due to the complexity of a bomb calorimeter, right? It's MC delta T plus the heat capacity of your bomb calorimeter times the change in temperature, okay? And why do we use bomb calorimeters? We can use them for gases, right? You'll use them for gases or any reaction that's extremely high in heat, right? Because as we know, coffee cups aren't the most safe conditions to run an experiment. Okay, this is just the last kind of review slide. So kind of touching on enthalpy. So we went over the definitions last time, right? So enthalpy is the difference in heat content between reactants and products at constant pressure, okay? It is a state variable, meaning the condition at the very beginning and very end matter, but how it got there, the actual path of the reaction, is irrelevant. And how would we calculate enthalpy? Well, we'll get into this a little bit more in a little bit, but the change in your enthalpy, delta H, would be equal to the enthalpy of all your products minus the enthalpy of all your reactants, okay? And if you get a positive enthalpy change, it's considered an endothermic reaction, right? Meaning it absorbs heat. If it is a negative delta H, it's going to be an exothermic reaction. It's going to release heat, okay? Thermochemical reactions are just balanced reactions with a delta H value assigned to it, and you can use that delta H value along with the coefficients of your reactants and products to make a conversion factor. Okay, we went over that last time. And then lastly, Hess's law is what we just went over. The basic idea is you add reactions together to make a goal reaction, and you manipulate not just your equations, but also your delta H value, right? So if you flip an equation, you have to change the sign on delta H. If you multiply an equation by some number, you have to multiply delta H by that number as well. Okay. So let's jump in a little bit to the new material. So we're going to deal with phase changes and enthalpy of formation. Okay, and so something important to note about phase changes is that there's actually no temperature change throughout them, right? So on a theoretical basis, a cube of ice is at 0 degrees Celsius until all of it melts. Once it's all in the form of liquid water, then it can start to heat up. But until all the ice is goes from solid to liquid water, it's going to be constant at 0 degrees Celsius. Okay, and so what are our types of phase changes? Well, we have endothermic phase changes, which means they absorb heat. Okay, and that's like going from solid to liquid, which we refer to as melting. You'll also see it referred to as fusion, right? Kind of put those two terms together because that's going to be important in just a moment. And then the process of going from a liquid to a gas is called vaporization, right? That makes sense, making vapor, right? Gas. And so again, those are endothermic. And the reason for this is as you go from a solid to a liquid, you have more energy, right? More kinetic energy, which means to get that extra energy, you need to absorb it from the environment, okay? Endothermic, right? Think about boiling a pot of water. You have to use your stove to input energy to turn water into water vapor, right? Gas to get it to boil. Okay. Going in the other direction, however, we have exothermic phase changes. So from a gas to a liquid, we call that process condensation. And then from a liquid to a solid, we refer to that as freezing. Okay. But it is very important to associate the liquid to gas conversion as vaporization and the solid to liquid as fusion, okay? Because we will be using those shortly. Okay, so let's pretend we have a beaker with an ice cube in it, right? And we're measuring the temperature of the ice cube in an oven, let's call it a 200-degree Celsius oven, right? And we're tracking, again, what the temperature and phase of this ice cube is, okay, along with time, okay, so as time goes. So at the beginning, when we put the ice cube in, it's gonna stay as a solid, right? It's gonna be solid, a solid ice cube, and as time goes on, the heat is going to heat up the ice until it gets warmer and warmer and warmer, and then once it hits 0 degrees Celsius, that ice is going to start to melt, okay? The process of melting is what you're going to see as H of fusion, or your change of enthalpy while fusion is occurring, okay? And again, remember that that's the process of going from a solid to a liquid, okay? Your H, or your enthalpy change of fusion. Okay, and so your ice is going to stay at 0 degrees Celsius as more and more of it gets turned into liquid water. Okay, and then the very last drop is going to turn kind of from an ice crystal to liquid water. As soon as all of it's in the liquid phase, that water is going to start to heat up in the oven, right? So it's no longer melting. It is all liquid now, and it's going to slowly heat up, right? Heat, 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 heat. And then boom, you're going to hit, the water's going to hit 100 degrees Celsius, and it's going to start to vaporize, right? So H of vaporization is our enthalpy change we see while all the liquid is turning to all gas, okay? And so at 100 degrees Celsius, it's going to take a while. All the water is going to have to go from liquid to gas. But once the last drop goes from liquid to gas, then that gas is going to continue heating up until it eventually gets to the temperature of that oven. So I think I said 200 degrees Celsius. Okay, but this is your basic kind of like heating curve for, this is for water. Okay, and I think these diagrams can be extremely helpful for these problems we're going to look at. So let's look at one together. Okay, so you have you have an 8-gram piece of ice, and it's -7 degrees Celsius. When you put the ice in a cup and leave it for an hour, you find that it becomes liquid water with a temperature of 23 degrees Celsius. How much heat was absorbed in total? Okay, so the fact that they say how much heat was absorbed tells you that your Q value at the end should be positive, right? If it's absorbed the heat, it has to be a positive value. Okay, and you're given a change in enthalpy of fusion and vaporization. Okay, and so remember, the fusion would be from solid to liquid. Okay, and the vaporization would be if you're going from a liquid to a gas. Now, in this case, we're going from ice, solid water, to liquid water. So we shouldn't have to use this vaporization number, but we will have to use the fusion number. One other thing to note is we give you the specific heat of both water and ice. It is very important to note that your specific heat is dependent on the state of matter, right? So your specific heat capacity for water and ice are not the same, okay? And that applies to any other compound you see. And so be very careful about that. Okay, and so how do we actually solve this question? And so when you're first starting out on these problems, I recommend kind of drawing a diagram like this. I think it helps. And so kind of at the very beginning, right, we're at about -7 degrees Celsius. That ice is going to heat up to 0 degrees Celsius. Then fusion is going to happen where all my ice becomes water, and then my liquid water is going to heat up to the final temperature that was given, that was 23 degrees Celsius. And so I'm going to split this problem into 3 separate parts. The first is when the ice is, we have ice, right? So solid H2O. The second phase is when fusion occurs. And the third is when my liquid water heats up. Okay, and so each number kind of corresponds to the math down here. So I'm first going to pay attention to my ice. Okay, my Q, or my heat of my solid ice, would be equal to the mass of my ice, which was 8 grams, times the specific heat capacity of my ice, which was given as 2.05 joules per gram degrees Celsius, times my change in temperature, which again, change in temperature is final minus initial. Now, one of the reasons I really like a diagram like this and recommend drawing it, especially when you're beginning, is because it's important to note that your change in temperature here isn't your overall change in temperature. It's only the change in temperature while you are in the solid ice phase, which means the change in temperature is going to be from -7 degrees Celsius to 0 degrees Celsius. Okay, so the final temperature is 0 degrees Celsius minus the initial -7 degrees Celsius. And so my delta T would actually be +7 degrees Celsius here. Okay, and what I find is the Q, or the heat that I absorbed when going from -7 degrees Celsius to 0 as ice, was 114.8 joules. Okay, so that was my first component. Now my second component is fusion, going from solid ice to liquid water. Okay, and my heat, or my enthalpy change of fusion, was given as 6.02 kilojoules per mole. Okay, and so what I have to do to get my heat of the fusion step is just to convert my 8 grams of ice or water to moles, because realize that the units for this are kilojoules per mole. Okay, and it'll always be kilojoules per mole, or almost always. And so up here, I did 8 grams of water. I divided it by the molar mass, and I find that that is equal to 0.444 moles. Okay, and so I did 6.02 kilojoules per mole multiplied by the number of moles of water, and I learned that we had to absorb 2.67 kilojoules. Realize this isn't just joules, this is kilojoules of energy to get all my ice from that solid phase to my liquid water phase. Okay, and then lastly, how much energy did we absorb to get that liquid water up to 23 degrees Celsius? Well, the Q, or heat of my liquid water, is equal to my mass of water, which the mass should never change here when it goes from one phase to another. So my mass should still be 8. My specific heat of water, remember to use the one for water, so the 4.184 value. And then my change in temperature while I'm in the liquid phase is my final temperature, 23 degrees Celsius, minus my initial 0 degrees Celsius. And I find that the heat absorbed to heat up the liquid water is 769.86 joules. And so what is the total energy I absorbed? Well, it's the amount of energy I absorbed from step 1 plus step 2 plus my third step. And do be careful, some of your Q values for steps 1 and 3, for example, are in terms of joules, while my heat value for step 2 is in kilojoules. So just make sure that you change them all to the same unit and then add them together. And I find that we absorb a total of 3,555 joules. You could also write that as 3.555 kilojoules. Are there any questions on this problem?
God, let's go for
Sorry, I heard somebody. Was there a question, or were you just?
So I have a quick question.
Yep.
So if it said, instead of saying absorbed, if it said like, I think it's if it gave off, would it be the negative of the answer that we got?
So if they said, if I worded the question, how much energy did this give off? Really the question would have been wrong, because this problem, when you're increasing in temperature like this, you're always going to be absorbing heat. So the answer was always going to be positive. And that's just because it's heating up. If we went from 23 degrees Celsius down to -7 degrees Celsius, then your answer would basically be the reverse, and then your answer would be -3,555 joules. Okay, but in order for you to give off that heat, you would have to be decreasing in temperature. While this problem, we are increasing.
Okay, makes sense. So the absorbed is just because like we're increasing temperature basically.
Yeah, and they also, a lot of times, if they don't want to say absorbed or released, you'll see the word evolves a lot. Okay, because that just means they don't want to specify which direction the heat is flowing. They kind of want you to know that. And so you'll see the term evolves a lot. And just note that that's a placeholder instead of them just saying absorbs or releases.
Okay, thank you.
Yeah, no problem. Now, one question I have for you guys is, what happens if we did do the reverse problem? Can anybody tell me what we might have to do in step number 2? That fusion step, if we are doing the reverse problem, where we're going from 23 degrees Celsius down to -7. Anyone, any ideas?
No, but keep going. We're already behind.
You'd use the other rate that was given.
So the other one, the vaporization, is when you go from liquid to a solid, right? So we didn't get to a temperature that high yet. Okay, and so remember, kind of like in Hess's law, right? Oh, and somebody put a comment in, so we'll see. Freezing rate, freezing kind of, that is freezing when you're going from a liquid to a solid, but realize, okay, so the fusion that they give you is solid to liquid, okay? And they give you basically a delta H value, right? Delta H of fusion, okay? And so if you're going from a liquid to a solid, right, that's the opposite direction. You're basically flipping that reaction, okay? And so if you're going from a liquid to solid, you would actually just change the sign on your delta H of fusion, okay? And so when you're going from a liquid to a solid, your delta H fusion that you would use there would be equal to -6.02 kilojoules per mole, right? It's just like in Hess's law, when we flip in a reaction, you would do the same for fusion, okay? And if you were going from, if you were going from a gas to a liquid, right, that's the opposite of what vaporization is. And so you would just change your sign on this value and calculate it in the exact same way. Does that make sense to people? And that is a big thing that if I were making an exam question, I would actually go in the reverse way to see if students understand that. that, right, your delta H of fusion when you're going from a liquid to solid has to have the opposite sign as when you go from a solid to a liquid. But that's my comment on that. And challenge problem tonight does reflect on that. Okay, and so the last topic we're going to talk about tonight is enthalpy of formation. Probably won't take us that long to get through. Basically, what that means is how much the enthalpy, like the value of it, is how much enthalpy is required to make 1 mole of some compound from its elements at 1 atmosphere and 25 degrees Celsius. Okay, and so unless you are being asked to solve for the enthalpy of formation of a single element, they will give you all those values. Okay, they'll be given in a table, and they'll be given in joules per mole or kilojoules per mole. Okay, and it's more likely it'll be in kilojoules per mole. One thing that I cannot emphasize enough is that this value is dependent on the state of matter. Okay, and I'll show you on the next slide, I believe, where we have an example, but they will often purposefully in a table throw in compounds to mess you up on exams, right? So maybe your equation involves steam, so gaseous water, and they might in the table also include liquid water to make sure you're paying attention and using the correct value. Okay, so your state of matter is very important. And again, people on exams sometimes sleep on that, but be hyper vigilant about those them trying to trick you. Okay. Note that the enthalpy of formation for any element in its natural state is 0, right? So hydrogen, if it's in a diatomic gas, or if it's H plus aqueous, those enthalpy of formations would be 0, right? Any of your diatomic gases, if they're diatomic gases, its enthalpy of formation 0. Any metal that's solid, 0. And typically, right, if you're trying to solve one of these problems and you're not given an enthalpy value and they're not asking you for it in the question, right, and you're like, where's that value? How can I solve it without that value? Double check. It's probably in its natural state. And the reason they didn't give it to you is because the enthalpy of formation for it is 0. Okay, and how do we calculate this? Again, the change in enthalpy for a reaction is equal to the enthalpy of all of our products minus all of our reactants. Okay, and so we're just going to jump right into a problem, right? And so what is the delta H for the following reaction, right? This is quite literally something they could ask straight up on an exam, and they typically do every year, okay? And so methane solid plus oxygen gas goes to CO2 gas in liquid water, okay? And they'll give you a table just like this. So you have all your compounds and enthalpy of formation values, okay, which are in kilojoules per mole. So again, I said, watch out for distracting information. Look, water here, I put the enthalpy of formation for if it's a gas or liquid water, and just note the values are different. So here we have liquid water, and so we want to be really careful in an exam to use the correct H2O value because it's liquid, not a gas. And they will put in some distracting information like this to throw you off. Okay, and so we want to find the delta H for this reaction. And so our delta H is equal to the sum of the enthalpy of all of our products minus the enthalpy of all of our reactants. Okay, and so here I wrote my chemical equation and I wrote the values from the table below it, right? So the formation of methane was negative 74.8 kilojoules per mole. Oxygen gas is its natural state, its standard state, so its enthalpy of formation is 0. Carbon dioxide is negative 393, and liquid water is negative 285.8. Now again, realize the units are kilojoules per mole, which means it's so important for you, down here when I actually calculate it, to multiply it by the coefficient in the balanced equation. Okay, so water, for example, the negative 285.8, we have to multiply it by 2 because its coefficient in the balanced equation is 2. Okay, and so what's our delta H for this equation? It's equal to the sum of all of our reactants, all of our products, right? So this is the enthalpy of formation of CO2 plus 2 times the formation of liquid water. We're gonna add that all together, and then we're gonna subtract from it all of our reactants, which in this case is just methane. And when you solve this, your delta H will come out to negative 890 kilojoules, okay? One note that I'll say where most people lose points on a problem like this is a lot of people will forget typically just how they write it on the piece of paper or plug it in. Don't forget to distribute this negative sign, right? You're subtracting all the reactants added together, okay? And so if there are multiple reactants, you need to distribute that negative sign appropriately. Okay. So jumping in, if anybody has any questions, I'm happy to answer them. If not, I'm just going to kind of scroll through the challenge problems. And if anything arises, I'm happy to answer it on any of the topics. So the first two, here they are. Pretty classic multiple choice questions. This is kind of relating to thermochemical equations. Okay. If you need a picture, I'm just going to skip to the next slide in about 3 seconds. 3, 2, 1. 3, just because it's not Chapter 5 gas laws, they do ask some theoretical questions about thermochem. So again, try to understand these topics, not just what equation do I plug it into, but, you know, what is enthalpy? How do different things relate? So for example, that which metal will heat up higher or like have a higher final temperature, that they could have given you less information about, right? They could have not given you a mass, and so you could have just had to solve it purely looking at the variables in the equation. So kind of understanding like that problem is good for theoretical questions as well. 4 is kind of similar to questions 1 and 2, but this is actually pretty much exactly how they delivered a question on my exam way back when. This would have been something that they had on the long answer section, right? So it's a little bit more similar to redox problems where it's not just what's your one answer. It's kind of like, given a situation, here are multiple different questions for you to try and get, right? So it's 4 different parts. Okay, number 5. I really like number 5. I think it's a pretty good problem. It is a thermochemical equation problem, but it kind of touches upon a question that was addressed on Mondays or in Monday's session. And so I'll kind of leave it there. I'll talk about that a little more next session. But I think number 5 is a pretty good problem to practice for thermochemical equations. Number 6 is one of those phase change problems, right? So I'm pretty sure I need to give you a lot of information for these problems, but I'm pretty sure this is everything you need to solve it. Yeah. Okay. One thing to know about number 6, I realized I said you put it in a freezer and it's cooled to 10 degrees Celsius. I think I meant to do -10, but I'm fine with 10 degrees Celsius. Do it as written, number 6, okay? Solve it as written. You'll just notice I gave you kind of some extra information. Here's another problem, kind of a heat exchange along with phase change. So I actually really like this problem as well. Just kind of allow you to take pictures. I'll go to the last slide in about 5 seconds. Okay, and here's the last question. It's basically just do the enthalpy, find the enthalpy change or the, the delta H for those 2 equations. And then question B asks question about hydrogen chloride. Okay, and that's gaseous hydrogen chloride, right? HCl, when it's in the gas, is hydrogen chloride. When aqueous, it's hydrochloric acid. But again, kind of just those enthalpy of formation questions, becoming more familiar with that. And if there's nothing else, I'm going to stop sharing to end the recording. But if anybody wants me to come back to any of these problems or go over anything, I'm happy to do so.